Welcome everyone. Really glad you can join us for this session of the Cloud Containers Conference at AWS. And today we're going to be talking about machine learning on Amazon EKS. My name is Mike Stefaniak. I'm a product manager on the EKS team, and I've been focusing on our machine learning efforts in the Kubernetes space. And later on, you'll hear from Jackson Shen, who is a software engineer on the EKS team who's been leading a lot of our open source contributions to the machine learning Kubernetes community. And so today I'm going to give a brief overview of machine learning on Kubernetes and EKS, and then we'll get into some demos, which is what I think people really want to see. And so we're going to cover 4 demos. One is EKS support for Inferentia, the Torch Elastic controller for Kubernetes, which is an exciting new project we've been collaborating with PyTorch on, a demo of how to run Spark on EKS, and then lastly, we'll dive into Kubeflow and some of the enterprise-ready features that have went into the recent 1.0 release of Kubeflow. So before we get into the demos, just real quickly, why containers, why machine learning, why Kubernetes? And I think before we get to Kubernetes, we need to talk about containers, because some of the same challenges that containers solved for microservice-based applications, which is packaging your dependencies in code together and solving the, it ran fine on my machine problem, it solves some of the same challenges for machine learning, where you might be packaging your training code, your dependencies, your configurations, maybe even some of your data together and run it in multiple places. And so on Kubernetes, there's really 3 things why machine learning has become so popular: composability, portability, and scalability. Composability is really what we just talked about, where you can package up all of your dependencies into a container, and that really allows you to separate the separation of duties between the data scientists, where they can run whatever library they want, and then the machine learning operations team, who can handle the Kubernetes cluster underneath. Portability, meaning you can run Kubernetes in an open source framework like Kubeflow on your laptop, you can run it on premises, and you run it on the cloud. And it makes it really easy to move your training jobs and inferencing endpoints from on-premise to the cloud. For example, when you need a lot more machines, you might not have them on premises, but if you go to AWS, you can scale to many GPUs in a cluster. And then scalability, that's really where Kubernetes and EKS excels. You can run hundreds, even thousands of worker nodes in a cluster, and you can iterate really quickly. So you might need to run a training model, tweak something, run it again, and the more worker nodes in your cluster, the faster you can iterate and train your model. And in an example machine learning workflow, it really ends up being multiple steps, from ingestion and analysis and data transformation, where you might use something like Spark, model training, where you might use TensorFlow or PyTorch, and then the actual deployment, where you run it on your Kubernetes cluster and serve predictions. And each one of these things and each one of these steps ends up being its own microservice. And of course, Kubernetes is great at managing container-based microservices. And when we think about the machine learning stack on EKS, we look at it at 3 levels. At the bottom level are really the machine learning frameworks in the infrastructure. So TensorFlow, MXNet, PyTorch, which all have AWS optimized versions. And then the infrastructure. So you have the powerful GPU-based training instances in the P3 family, and then inferencing instances, the G4, in the AWS Inferentia, which we'll talk about a little later. You also have storage abstractions like FSx for Lustre, which allows you to store your data, your training data in S3, and use that in a training job. And then we have the platform, the container platform, which is EKS, which allows you to scale to hundreds, or even thousands of worker nodes. And then on top of that are the different machine learning platforms that you can run on top of Kubernetes. So Kubeflow, which is one of the more popular machine learning frameworks on Kubernetes, which we'll talk about a little later today. And then other things like Elastic Training, which we'll also get into. So with that, let's jump right into the demos. We're going to jump into our first demo here and talk about EKS support for EC2 Influence instances, which feature AWS Inferentia. Amazon's first custom-built chip for machine learning. Our customers have told us that inferencing, or rather prediction against a trained machine learning model, can account for up to 90% of costs in the end-to-end machine learning lifecycle. And when you think about it, it makes sense because you may have a model that only needs to be trained once a week for a few hours, but the application that is serving predictions needs to be running 24/7. And in a desire to create ever more rich applications for end users, data scientists and machine learning practitioners are developing more sophisticated models. And to run those models in production, it gets more and more expensive. And that's why we built Inferentia and delivered them on EC2 Inf1 instances. Compared to the G4 family, which was already the lowest cost inferencing in the cloud, you can get up to 40% lower cost per inference and 3 times more throughput using AWS Inferentia on Inf1 instances. And Inf1 instances are designed for a wide range of machine learning inferencing applications, from fraud detection, image recognition, natural language processing, and you can lower the cost of running those types of applications in production. In order to get started, you also need to use AWS Neuron, which is the software development kit that comes along with Inferentia, and that provides both the runtime, it provides the runtime as well as a compiler. So you compile an existing trained model and you can run that against an Inferentia chip. To support Inf1 instances on EKS, we had to do 2 main things. One was update the EKS GPU AMI, which we now call the accelerated AMI. So when that AMI loads up, it'll check if it's a GPU instance and it'll load the GPU container, NVIDIA container runtime. If it's an Inf1 instance, it'll load the Neuron container runtime. The other thing we had to do was build a Kubernetes device plugin. If you're familiar with running machine learning workloads on GPUs, you're familiar with the NVIDIA device plugin. And so a similar vein, we built the Neuron device plugin for Inferentia. And when you run that in your cluster, if an Inf1 instance gets started, it'll inspect that, figure out how many Inferentia chips are on the instance, and advertise those to the Kubernetes scheduler. And so in this demo, we're going to do 3 things. We're going to first take a model and compile it using the Neuron compiler. We're going to push that to S3. And then we're going to take a look at a deployment manifest, a Kubernetes deployment, and deploy that into our cluster. That'll load the model from S3. It'll use TensorFlow serving, and it'll spin up a prediction endpoint. And then we'll use a simple Python file to run a bunch of predictions and check out the performance. So let's get started. The first thing I'm going to do here is I've already logged in. This is a AWS Deep Learning AMI, and it's running on a C5, I believe C5 4X large. So it's a relatively powerful instance, which we're going to use to compile our model. The Deep Learning AMI becomes pre-packaged with the Neuron SDK. So if you see here, I've activated this Python virtual environment. And let's look at the packages in here. And there's a bunch. But the one we're most interested in is this TensorFlow Neuron package. So the Neuron SDK works with all the popular machine learning libraries. So that's MXNet, PyTorch, TensorFlow. In this example, we're going to use TensorFlow. So then the next thing we want to do is actually take a trained model and compile it using the Neuron compiler. So if we look at this Python file, which is relatively simple, you can see that we're importing this particular model, which is a ResNet model. I won't get into the details in this demo, but it's a model that's designed for image processing. So it's a deep learning model which can take advantage of something like the hardware acceleration that comes with an Inferentia chip. You feed it a bunch of images, and the model is going to do its best to predict what's actually in the image. So when we look here, we can see we're importing the ResNet model, and then the main function here is we're taking the compiled model and we're using this TensorFlow neuron compiling step. And the TensorFlow optimized library the neuron optimized TensorFlow library has the same APIs as the regular TensorFlow, but behind the scenes it's going to optimize it for neuron. And so if we go ahead and run this, you can see that this neuron compiler is taking the trained model and doing the compiling step. And so I have another tab open here in the same instance, and we can see that the Python compiler script is using up all of the CPU on the instance, and it's compiling the model. Now this will take a few minutes, so I went ahead and compiled it ahead of time. And if you look at the output, you can see that this saved model file, and that's what TensorFlow serving is going to expect when it loads up and loads a model used for serving. And so the next thing we would do once we have this trained model is send it to S3. So using a command similar to this, where we'll sync the model directory to S3, which I've also done ahead of time. So let's take a look. In the S3 console, we can see here's our model. And we've just transferred the saved model that was on the deep learning AMI into a central location in S3, so the informed instances in the EKS cluster can use it. So now we have our compiled model, and we have it saved in S3. Now we need to create an EKS cluster using informed instances. And the easiest way to do that is using EKS Cuddle, which is the command line tool for EKS. And so here's a sample configuration file for EKS Cuddle. It's here you can just see I'm giving my cluster name of Inferentia. I'm using Kubernetes version 1.16. I'm using the US West 2 region. And down here I'm specifying my node group. And so you can see the instance type I'm using is an Infont 2x large. And this includes a single Inferentia chip. I want 2 instances in my node group. And then the other thing to note here is typically the worker node policy, the CNI policy, and the container registry policy are required on any worker node in EKS. I'm also attaching the S3 read-only policy so that my TensorFlow serving application can read the model from S3. And so what I would do with this configuration file is I would come over to my terminal. I'd do something like EKS Cuddle, create cluster. I'd run that command. That will take about 10 minutes or so. So again, ahead of time, I went and did that. If we log in to EKS, into the EKS console, here is my cluster that got created. To continue using this demo, I'm going to use a tool called Lens, which is an open source IDE for Kubernetes that lets you visually inspect a cluster. And so when I go into my cluster here and I look at the nodes, I can see I have 2 Inferentia nodes. You can see the labels here, instance type inf1 2x large. The other thing to note is that EKS Cuddle recognized that we were launching a cluster with inf1 instances, and it went ahead and installed the Neuron device plugin for us. So this is the device plugin. It's installed on my cluster. If we go back and look at one of our nodes, let's describe the node. And if we look at the allocatable resources, here you can see, well, you can't see that. Here you can see there's one Neuron device that's advertised on the instance. And so this is available. The Kubernetes scheduler knows this. And so now we're good. We have a cluster. The device plugin is running. We have 2 inf1 instances. Now we're actually ready to deploy our application. So let's come over and look at our deployment file. And there's a couple things. This is a pretty standard deployment file, but there's a couple things we want to note. The first is the application container. So in this case, we're pulling down this TensorFlow model server Neuron. I went ahead and built this file myself. So if we look at this very simple Docker file, we are importing the Neuron yum repository, and it's just a single command to install the TensorFlow model server. Eventually, the TensorFlow model server optimized for Neuron will be part of the Amazon deep learning containers, but that's still coming soon. So for now, I built my own container and uploaded it to ECR, which is Amazon's container registry. And so we have our container. We're starting up the model server, as you can see, and then we're setting the base path to the S3 bucket that I showed you earlier. And so this is the actual model that we compiled before. The other thing we want to note is, so the Neuron driver actually runs as a sidecar container. So it's not built into the AMI itself, but it runs as a sidecar. And you can see down here, this is where we're actually requesting the Neuron device. And so these 2 containers talk to each other over a Unix socket, which we set up here. And this is my deployment file. So I'll go back and apply this to my cluster. And we should see, so we have two new pods created. I created 2 replicas in this deployment. Everything's running, so let's check logs here. We can see my TensorFlow model server started. It found my model, and it's serving it at this address. The other thing we want to do now is actually expose these pods behind the deployment as a service in Kubernetes so we can actually talk to it. And so we have another simple file here where we're just taking the pods that are behind the deployment and exposing them as a simple service in Kubernetes. So we'll go ahead and deploy that to the cluster. And that was created. Let's go check. Looks like it started using this internal cluster IP address. So that's it. Now our application's running. Let's actually make some predictions. So to do that, the first thing we're going to do is we're just going to use the port forwarding feature built into Kubernetes so we can access this cluster IP service locally. Running this in production, you'd typically expose your Kubernetes service through a load balancer so an application outside the cluster could access it. For here, we're just going to use the simple port forwarding. So I'll go ahead, start that in my cluster. And the last piece we want to do to make sure everything's working is actually send some predictions against our service. So I've created a simple Python file here. It's using the localhost port 9000, which we just exposed. And it's loading this image. So this cute little kitten, we're going to send this as a prediction request to our model, and let's see what it does. So I have the code down here, which is just going to take that in, send it to our server. So let's run this, see what we get back. And there we go. Our model predicted a tabby cat with about a 70% probability, a lynx about a 10% probability, a tiger cat, which I'm not quite sure what that is, which a little less probability. So that's pretty good. But to actually see what kind of performance we can get, let's actually run a bunch of predictions through our model. So let's say run this through 30 times and see what kind of average latency we get. For an application like this in production, you'd also typically batch up these requests and send them as one request rather than individually. Here we're just going to send each prediction request individually. And here we go. You can see them going through. This is pretty good performance for a ResNet model. And there we go. We're averaging about a half a second latency. And so that's it. We've just taken a compiled TensorFlow model, run it through the Neuron SDK to optimize it for inferentia chips. Then we started our EKS cluster, ran with Inf1 instances, deployed our TensorFlow model server, and then ran a bunch of predictions instead. And so that's how you can use inferentia with EKS. We have a lot more information in our documentation, and we're excited to see what our customers are going to build. On to the next demo. We've been talking a lot about inferencing, but we're going to get into training here. We're excited to talk about a new project that we've collaborated with the PyTorch team at Facebook on called the Torch Elastic Controller for Kubernetes. One of the challenges with machine learning training is compared to, say, a normal microservice application you run in Kubernetes, is that with the normal application, when a pod goes away, typically another replica comes up and your application continues serving traffic. With machine learning training, if you lose a worker node, for example, typically you have to restart the entire job. And that can become very painful if you have a training job that's running for 3-4 hours, sometimes even longer. And so PyTorch developed a new library called PyTorch Elastic, which is designed for deep learning, fault-tolerant, and elastic training. Which one of the big benefits is that you can run training jobs on EC2 spot instances because your training job can now tolerate failures. And so what we built is a Kubernetes native controller that implements the PyTorch Elastic interface and spins up all the pods and services needed to run a PyTorch Elastic training job in a Kubernetes cluster. And so we're going to run through a quick demo here to simulate how you can start a training job, and then if it was running on spot instances and one went away, how your training job would just continue to run. So I have another cluster I've created ahead of time, and in this case, I used EKS managed node groups to create two different node groups. One is just a node group with one instance with a small, I think it's a T3 instance in it. And then another one with node group of two Amazon EC2 P3 instances, which are designed for training. And I'll get to why we need both of these in a minute. So I'm going to go back to my IDE here. And the first thing I'm going to do is install the controller and the custom resource into my cluster. So how the Torch Elastic controller for Kubernetes works is the controller runs in your cluster, and it watches a custom resource definition that's also installed. And in that custom resource definition, you define the minimum and maximum number of workers that you can have as part of your training job, and the controller manages the pods that you define in there. So I've downloaded the Torch Elastic GitHub repository locally here, and to install the controller, you just run, I'll run this command. And you'll see it'll create a new namespace, role bindings, the custom resource definition, and then the controller itself. So we should see here the controller got installed in this namespace. Let's filter this down. And we can see that the Torch Elastic controller started. How PyTorch Elastic works is it has a component called Rendezvous, which is responsible for maintaining the membership of the workers that are part of your training job. And the recommended backend for Rendezvous is etcd, which is the same backend that Kubernetes uses. And so what we're going to do is install just a single etcd instance into our cluster. So we have this file here, and you'll notice that I have this selector on here because I'm going to make sure that the etcd instance runs on the T3, which we would run as an on-demand instance, versus having it run on the P3 instances, which could be spot and may go away. So let's apply the etcd instance to the cluster, and you can see that's up and running. Let's check the logs. Looks good. Looks like we started. And now let's launch our training job into our cluster. So this is the custom resource. It's called Elastic Job. And what we're doing here is defining our Rendezvous endpoint, which in this case is just a local etcd service we just created. I'm defining the minimum and maximum number of replicas that should be able to run in this training job. So in this case, minimum of 1, maximum of 3, and we're going to start with 2 replicas. And each replica is requesting a GPU, and I currently have 2 GPU instances in my cluster, so this should start. And in this case, for the training container, we're just using the built-in Torch Elastic example, which I believe uses an ImageNet model to train. So let's go ahead and apply this to our cluster. Whoops. And we should see 2 workers start here, 2 pods. And so in this case, the controller was watching the custom resources called Elastic Job. It saw one was added to the cluster, and went ahead and created the pods needed for training for us. And if we look into the logs here, we can see that the training job is starting. You can see that the logs here are mentioning the rendezvous state. So rendezvous is keeping track of the number of workers in my training job. And so now our training job is chugging happily along. And let's simulate if we were running these on spot instances and one of them got taken away, what would happen? So I go back to my cluster here, and I'm going to go into my P3 node group, and I'm going to change the capacity down to 1. And what that's going to do is take away an instance out of the cluster, which is similar to what might happen if you're running on a fleet of spot instances and one of them gets taken away. So let's go back and look here. We can see our training job is started. It's running through a number of intervals here as part of the model training. So you can see it's 260 out of 1500. So it still has a little bit of ways to go here. Let's refresh our node group. And we can see that in our node group, we now are down to a single node. And we'll look back in our cluster, and you can see that one of the nodes is already, it's scheduling disabled, and eventually it'll be removed from the cluster. Now in a normal training job, this would mean the job would fail. And if you had a job running for 3 hours, you'd have to restart the entire thing. But let's go back and check. And you can see that one of the workers went away. It's now pending because there's no node in the cluster for it to run on. But let's take a look at our other one. And it looks like here is where the instance went away. But it looks like Rendezvous spun up. Or rather, Rendezvous realized that the Rendezvous component realized one of the nodes left the cluster. And it looks like another Rendezvous happened. And sure enough, our job continues to train. And this is a pretty powerful component, right? If you had a job that was running for hours and even days, uh, your job can tolerate failure. So you can run on spot instances, save money. If you're a machine learning team, your data scientists are happy because your training jobs are going to finish faster and they won't ever have to be restarted. And your finance department is going to be happy because the GPUs in your cluster are always being put to good use. So that's a quick demo of the Torch Elastic controller for Kubernetes. Some ideas for future improvements we have are automatic worker resizing and adding a concept of job priority into the Elastic Job custom resource. Thank you all very much for listening. I'll now hand it off to my colleague Jackson for a few additional demos.
Hi, hello everyone. This is Jiaxin. I'm a software engineer in AWS EKS team. So today I'll walk you through two examples. One is the Kubeflow on EKS. The second one is the Spark on EKS. So let's go to the first one. So I already have a cluster deployed with the Kubeflow, and this is the login page of Kubeflow. Here we use the DAX for authentication. You can definitely use other tools like AWS Cognito to connect your user pools as the alternatives. Let's log in the cluster. So this is the central dashboard of Kubeflow. There's several components, and we'll introduce notebooks and the pipeline today. So in the notebook servers, you can create a notebook as your IDE. So we will show this demo from a data scientist point of view today. So there's different options you can configure based on your needs. For example, you can use the custom image. You can specify the resource for the notebooks. You can mount any volumes here. So in AWS, EFS and FSX for Luster can be used here. Definitely, GPU is also supported here. I already have the server created. So let's go inside the notebooks. So in the notebooks today, I'll show two small demos in Kubeflow. So all the source code of this repo actually come from GitHub repo AWS samples EKS Kubeflow workshop. So the first part I like to show is how Kubeflow Fairing simplify your model development. And Fairing is the component to streamline the training, model development, and inference in the notebooks for data scientists to use. And it's very easy. Let me show the detailed steps. So this problem is actually very straightforward. It comes from the cargo computations. So the model, we need to build a model to predict the house prices using regression algorithm. So in this case, we will build an XGBoost model in the local notebook server. And then we train an XGBoost remotely on EKS. And after that, with the trained model, we like to deploy an inference server. And then we can call the inference server to get some prediction results. I already installed the dependencies. I think we can start from developing the model. So I won't talk too much on the model details. It's very straightforward. We use the XGBoost regressor and train a model here. So we feed the data in this method. And after that, we have an evaluate model to do the prediction based on the feature data we passed in. So we have a high-level class to wipe those methods. There's a train method and predict the method can be used later. So this is the algorithm. And then we just run these cells. We can see this algorithm runs successfully, and we can see some logs. So all the training happen inside the notebooks. So what if you have more data like to train with more resources? How can we do that? Traditionally, you need to use the you need to build a Docker file, and then put your model there and build a image, container image, submit to container registry, and then write a Kubernetes YAML file to submit to the cluster and monitoring status. So Faring is aims to solve these problems, and it streamlines all these processes and very easy to use. Let me show you here. The first thing, we need to build a S3 bucket to store some Faring build files. And once we get the bucket, we have some auxiliary code to come up a Docker registry. And then we build a Kubeflow AWS backend. So the backend will do a few things. First thing, it will build the container image and then write some metadata to S3. So after that, with the image built, we will pass the image to ECR. And here, as you see, the different part from your local training is we import a train job here. We pass the algorithm you built here. And we also pass the dependency files. And the Docker registry we just built can be used here. And then we pass some build context at the backend. Then we just build these training jobs. It actually takes some time to finish. Let's check the backend side. Yeah, as you can see, there's one Faring builder pod just created it like 10 seconds ago. So that's the build context, and that will help build the image in the background. And this takes a few seconds. So it will stream all the logs to the Jupyter notebooks. And I can explain the next steps at the same time. And then we can go back to check the result. So once we have a built model, so next step, we can do some testing. So here with the context, we can deploy a prediction endpoint using the code you just built. And the prediction endpoint, we can configure a lot of details for your inference server. For example, here we read from the Docker registry. You just publish the model there, and then we can specify the Kubernetes service type. And still, we need to pass the context here. And after that, we can create an endpoint. So let's see here. Is still building the files. Let's check the ECR. So the Faring job is the repository we like to use. So here has some historical image tags I submit there. So this one should finish soon. Okay, we already see that. Yeah, it actually finished. So it kick off a job on Kubernetes cluster and finish training jobs. And as we can see, yeah, so the image already been uploaded here. So the next we deploy the model. It will use the image we just built and deploy it as the deployment and the service in Kubernetes cluster. So this is the inference builder we just deployed. So you can see that it's very straightforward, and data scientists don't need to jump to like terminals or use Dockers. it doesn't need to have those knowledge to develop their model and deploy them in Kubernetes cluster. Everything is very friendly to data scientists. And the good thing is data scientists can verify all the models and then ship to some like DevOps for large scale deployment in productions. Everything can be done inside the notebooks. Um, yeah, let's wait for like 1 minute. So after we have the inference server, we can call the prediction endpoint to verify the model's like prediction results. So I'll show it later. Okay, since the endpoint is already ready, so we can copy the endpoint here and pass to this block. Okay, we successfully get the prediction results. And after that, we can definitely clean up the endpoint, etc. We can do some cleanup later. So the next part I like to show is how to productionize your machine learning workflow. So go to the pipeline examples. So this is the mainest example. So everyone should be very familiar with that. And the first step, we installed the KFP like library. So KFP is the Kubeflow Pipeline SDK, Python SDK, which will be used here to submit the workflow. Yes, I will just go through the examples. And in these examples, we will train a model and deploy it as a UI service we can query later. Let's see. So here we need a S3 bucket to store the persistent model and specify the regions. So this is the Kubeflow pipeline. So with the container image, you can actually productionize the workflow and run it periodically. So in this example, the first part, we launch hyperparameter training jobs. So it will help us choose the best batch sizes and like learning rate. So you can see the range here. And the second step, with the best parameters, we create a TensorFlow training jobs. And the training jobs will persist the model to S3. And the last step, we create some model inference servers powered by TensorFlow serving, and we can check the results later. So this is the pipeline details. After we define the pipeline, we can create like a run from the pipeline functions we just defined. Okay, it gives us two links. The first one is the experiment link. The second one is the run Kubeflow pipeline run. It actually takes some time, so I will use the past pipeline to talk about the process. So this is the one I just finished. As I said, the first one, it passed the some parameters there, and then the output will be the best learning rate and the batch size. And with these parameters, we pass those as the input to the next step, which is the training job launcher. So the training job will give us the model, persist the model in S3. And after that, we'll use this model to deploy a service. It is the deployment and the service in Kubernetes. And this is, we at the same time, in parallel, we also deploy a UI service and like UI deployment so we can visualize the results. Come back to the notebook. So manage the service is the service we just deployed there. So we can verify the results here. So all these code snippets are just read the data set and populate one data set, and then call the inference endpoint. And let's check the results. So as you can see, we pass the feature vector to the endpoint service, and the model predict this belongs to class 3, and actually it was actually a class 3, so the prediction is correct. And let's go to the UI service to have a see. So, as you can see, this is the Minister model server. We actually connect to the service we just deployed. And then it shows some task results here. So that's the choose and the prediction. We can check for some random pictures and get the results. So everything's correct. So this is the Kubeflow pipeline, and you can use it to orchestrate your machine learning workflows. And come back to the UI link. Wait a minute. Yeah, actually, you can use some native like Kubernetes component, or you can use some cloud components like SageMaker. So there's no limitations, and it's very flexible. In our case, we used Kubernetes native components like Cartib, hyperparameter training, and TensorFlow operator to train your model. And the deploy side, we used TensorFlow serving on Kubernetes directly. But as an alternative, you can definitely use like SageMaker HPO, SageMaker training, or SageMaker inference. Okay, so that's all the demos for Kubeflow. Next, we will show the Spark use case. The second example I like to show is the Spark on EKS. Spark on Kubernetes become very popular recently because Kubernetes have a lot of capabilities Spark can leverage. For example, like namespace, container level orchestration, and it also helped to improve the resource utilization rate. And today I'll show some demos to run the Spark applications on EKS. All those codes and examples come from our blog post and samples. We have a blog post talking about optimizing Spark performance on Kubernetes. It covers most of the critical stuff to run Spark on Kubernetes. You can have a check later. So the code is here from AWS samples EKS Spark benchmark. Let's come back to the demo. There's two ways to submit the Spark applications in Kubernetes. So the first way is the very Kubernetes native way. And the Kubernetes user should be very familiar with the custom resource concept. So this is operated by Spark operator, and we can define a custom resource Spark allocations. And after that, in the pod spec, we can specify, okay, the container image we like to use, and some arguments, and some Spark configurations. In this example, we would like to run a Java word count examples. So the argument file is just one like configuration file in my S3 bucket. So this is the first way. So the second way is the Spark. Traditional users should be very familiar with that. It used the Spark Summit command, and the only difference part between the YAR and Mesos part is we pass the Kubernetes API server address here as the Spark master. Besides that, there's some Kubernetes specific configurations here. For example, you can specify the container image, and you can specify the pod name for the drivers, and the Kubernetes namespace, etc. Okay, let's run. Let's try to run those examples. So this is the Spark Summit. We can create the applications here. So as we can see, it creates the pod called word count S3 shell. It is the driver pod. And the driver will talk to API server and request some resources to launch the executor pod. It is running. And we can check the logs here. So yeah, because my file is very small, it just calculate the count for every word and just return. Let's try to run the second way. So the file called Spark word count operator. Let's submit this job. We already have the Spark operator installed in other namespace, so this job should be picked up by the operators. So we can see there's a new pod called word count S3 operator. So the driver is up. I think after a few seconds, yeah, the driver requests a few executors here. Yeah, so that's the two ways to submit Spark workflows. And I like to show some basic monitoring of Spark. So we have another job called Spark Pi here. So it is very simple. It's just a Pi example. And let's check the driver pod. So the driver is up. So we can pod forward the like 4040 on driver pod to check the Spark application UI. Let's go back to the browser. Yeah, we can see the Spark jobs stages here, and we can check the Spark application environment and all the executor status here. So the job application UI won't be available after the job finish. To persist those job histories, you need a Spark history server. Okay. Yeah, so that's two ways to submit the Spark jobs. I like to show another way to submit the Spark jobs in Jupyter Notebooks. I already have a pod deployed here, and I pod forward 4.8 port to my local browser. Let's have a look. Besides the batch workloads, a lot of users use Spark Shell to do some interactive queries. We like to show this case. So that's the client mode. The difference part is we specify client as the deploy mode here. By default is cluster. So once we specify client, that means the driver will run inside this notebook pod, and it will request resources in Kubernetes cluster, and the executors will connect the notebook pod. Let's try to run this example. Here we create a Spark context. During this process, it will create some pods here. Let's have a check. So those pods will be long-running pods. It will be destroyed only if we destroy the Spark context. And here we can run some code, and it will submit to those executors. Okay, we can see we get the results here. After we finish, we can stop the Spark context. Once we check the pause here, so it will be terminated. Yeah, so that's all the demos I like to show. As you can see, it's very easy to run Spark on Kubernetes, but that's not enough because in order to run some production level workloads, you need a lot of things, not just like this basic use case. You need like a Spark history server, some Hive servers as well, and some orchestration tools like Airflow. We like to do some work in this area and contribute back to upstream. Yeah, that's everything from my side. Thank you everyone joining the session. And if you have any questions, feel free to post the questions in the chat window and enjoy the rest of the conference. Thank you.